All right, yeah, so this handout, we're actually going to go through some of the graphs at the bottom of it. So the trig stuff, we will actually do a unit on trigonometry, so I wouldn't stress on this stuff right now. Unit 2, we're going to talk about logs and exponentials, so I wouldn't worry about this right now. But the stuff up here, the circles, obviously we've done, and then these graphs here, we're going to actually look at in Unit 1. But these are kind of what we call base graphs. So these are really, really common graphs. Notice they're the most simplistic form of the graph. So like a lot of the intercepts are at the origin. It's just as basic as you can possibly get. The coefficients are 1. And so these are really, really important because what we're going to learn today is shifts and translations of graphs. So a graphing technique, and I kind of mentioned this earlier, alluded to it, that, you know, when I look at a function, sometimes if I recognize the base graph that it's based on and I see the moves with the way the equation's structured, it's really, really easy for me to draw the graph without putting it in a computer, because all I have to do is take the base graph and just slide it left, right, up, down as needed. And so that's what we're going to talk about today. How do you look at an equation and then just know, based on what you're looking at, how to shift and move it around. So just make sure I would hang on to this. It's a great quick reference guide, and we like I said, I still give it to the calculus students because a lot of students forget these, but pretty much every math teacher from every class you have after this one would just expect you to know all of these like the back of your hand. If you saw the equation, they would expect you to just be able to sketch these graphs. So they're really good. They're useful. And that's probably one of the number one questions I used to get asked, like what's the list of all the pictures I'm just supposed to know? So I think those are pretty standard. Okay, so what we want to talk about today is that there are certain things within the function we can look at, and it's going to tell us what the equation is doing to that function. So the easiest thing to kind of talk about, and a lot of people tend to remember this, is if we want to shift a graph. And a shift and a translation, right? Those are usually interchangeable words. So if we say we shift it 2 units up, someone else might say they translate it 2 units up. So those 2 words tend to get used interchangeably in math. So if you have a function f of x, and we add any constant value to the outside, this takes the original graph and shifts it c units to the right. So adding something on the outside moves you to the right. And that's kind of easy to remember because the right is the positive x direction. So if you're adding values on the outside, oh my God, guys, I'm the worst person. It's up. I'm the worst. As soon as those words came out of my mouth, I realized what I said. When you're adding on the outside, you're adding to the y value. And so the positive y direction is up. So adding on the outside is going to shift you up. Okay. Similarly, if we subtract c on the outside, right, that will shift the graph c units down for the same reason. So what you're doing there is you're subtracting that number c from every y coordinate on the graph, and so it's going to slide it down toward the negative y direction. Right? Now on the inside of the graph, and you're going to see when we get a little bit deeper and we start doing more domain and range problems algebraically, you'll see what we do to the inside of functions appears to have the opposite effect of what it should, and that has to do with algebra. So when we actually do some domain and range problems where we manipulate the domain, you'll see that when we what it looks like inside the function will actually have the opposite effect, and when we calculate domain, we have to use algebra to do that. And you'll see when you're solving for x, every time you make a move when you're solving for x, you're kind of like unpacking things, right? So if you have a 2x, right, and you want to solve for x, you divide by the 2 that's being multiplied, right? Because you have to undo it. if you have x plus 3, right, equals some value, you have to subtract a 3. So that's why when we look at things on the inside of functions, because of algebra, it appears to have the opposite effect. So, and what we mean by the inside, right, if I plug in x plus c on the inside of a function, right, some people would see the plus sign and be like, oh, it must shift it to the right. It's actually going to shift it to the left. If we put x minus c, it will shift us c units to the right. So things happening inside the function have sort of the opposite effect of what they look like. Okay. If we multiply the outside of a function by a constant, well, when we added c to the outside, right, it made all the y values bigger, so things moved up. If you multiply by c on the outside, well, if c is a number bigger than 1, right, it's going to make all the y values bigger. If c is a number bigger than 2, it's going to make all the y values smaller. So what multiplying by c does is it stretches or compresses f of x vertically by a factor of c. So for example, if c is 2, right, well, it's going to double every y value. So all the y points, like if a y value is 1, it now goes up to 2. If a y value is 2, it now goes up to 4. So it's going to be like grabbing the graph and stretching it this way, vertically by 2. If c is 1/2, right, it takes every y value and cuts it in half. So that would be like compressing the graph by a factor of 2, right, or a factor of 1/2, depending on how you want to describe that.
But it only does the y values?
Yeah, because it's happening outside the function, right? Because if you actually look at this, right, nothing happens to the x's you plug in, right? It's when the y's come out, then we make the adjustment, right? But if we put c on the inside, right, now we're multiplying the x value before we ever even plug it into the equation. So what this is going to do is it's going to stretch or compress the graph horizontally by a factor of c. And it should have the opposite effect of what you think. So putting a 2 inside should actually compress it by a factor of 2. And when you put a 1/2 inside, it should stretch it. So the reason that happens is we're going to look at a domain problem, but so any one of these moves you make, by the way, that affects the inside of a function, right, only affects the domain values. The domain would adjust accordingly, right? Anything up here that we do to the outside of a function is going to affect the values of its range, right? Because domain goes in, range comes out. Right? The other thing that we can do to graphs is we can reflect them. So one way to kind of think about reflections is really we're flipping them over something. And so the reason they call it a reflection is if you drew the original graph and the reflection on the same graph, they would look like mirror images of each other over a line. So if we multiply, right, f of x by -1 on the outside, right? So the outside things affect the y values. So you are taking every y value and you're multiplying by -1. So if all the y values were positive, they would now all become negative. And so what we would say there is it reflects over the x-axis. So you can kind of imagine if you take your paper and fold it on the x-axis, it's just going to flip it over and fold it there. If we multiply by -1 on the inside, Well, now we're taking, if they'll say the x value was positive, you're taking every x value that was on the right side of 0, immediately taking it over to the negative side of 0. And so what this does is it reflects f of x over the y-axis. So what's kind of a little crazy here is any one of these moves can be made in any combination. Well, let's say this. We can do any one of these things to a function in pretty much any combination we want. So we can take a graph and flip it over both the x and the y, shift it left. I mean, the only thing you can't do is shift it left and right, right? You can't shift it up and down. But we can shift something vertically, horizontally. We can reflect it over an axis, and then I can multiply it by a constant if I want and stretch it. So one of the things you want to make sure that you understand what all of these different things are doing, because we can do them in any combination we want. Now, as far as when it comes to graphing the new function, okay, when you do algebra, right, we have an order of operations because we want to make sure that everybody gets to the same place, right, the same answer. So there's a structured order, right? Please, my dear Aunt Sally, if I remember that. So same thing's kind of true here. You can do the moves in any order you want as long as you do all the reflections before you do any translations, okay? So always perform any reflections before translations, right? As long as you do that, you can do them in any order. So if I have a graph that I want to reflect over the x and the y, and then I want to shift it up too, okay? So it doesn't matter whether I flip it over y or over x first. I can do the reflections in any order. I just have to do all the reflections first. The translations, it doesn't matter what order I do the translations in. I can do them in any order I want as long as I do them after I do the reflections. So all the reflections first, and then all the translations second. All right? So let's look at an example. And so one of the things they'll do before we get into the actual equations and formulas is we'll just have you explain what's going on with graphs. So we might give you a graph of some arbitrary f of x and then ask you to identify the new graph after we've done these moves on it. You won't even know the equation of the function. Or sometimes we'll just give it to you in an expression. So if I had something like this, we'll say this is y equals. Right, and so we want to know, well, how does our new graph y relate to the original expression f of x? So this one, there was no reflections, right? There's no negative sign on the outside. And on the inside, what you want to look for is, if it's just negative x on the inside, then clearly they're wanting you to do a flip, right? But what if I want you to flip it over the y-axis and shift it left or right, right? What was that going to look like? So you could see something on the inside like negative x plus 3. We usually don't write things like that. What they would probably do is reverse the order of that and say 3 minus x. So when you're on the inside of a function, if you see a negative or a minus sign right in front of the x values, that means there was a reflection happening on the graph. So in this case, the x is positive out front. There's a positive 1 is the coefficient, so there were no reflections in this graph. So f of x, and we can do these in any order we want. We can list them out, right? Was stretched vertically by a factor of 2, right? It was shifted 3 units right and shifted 5 units up. So if you go back and think about the circle equation for a second. So the circle equation, we had an h and a k, right? And it was x minus h quantity squared, right? Plus y minus k quantity squared. Well, if you look at that now through this, the minus h and the minus k was actually shifting the circle, right? So that's why when we plugged in, if you had an x minus 2, the coordinate of the center was positive 2 because x minus 2 shifted the circle to the right 2, right? And then the y minus k was shifting it up, that value of 2 when you're talking about a circle. So that's all it is in that formula. It's another way of thinking about that formula, and as opposed to the distance formula when you look at the center, is it's, oh, well, instead of being at the origin, which is where the base graph is, you shift it left, right, up, down based on the pluses or minuses in the equation. All right, so before we go on and do some more examples, I want to take a quick second to talk about absolute value because it comes up a lot in this section. And it's one of those things that a lot of people tend to struggle with, and you will see absolute values again in calculus, and you want to make sure you understand what's going on. So the function, right, the absolute value of x, a lot of people might remember, right, that it just looks like a V. Right, where this is 0, 0. Most people, if you ask them algebraically to interpret an absolute value, if I said, what's the absolute value of 2? Most people tell me 2. If I said, what's the absolute value of negative 2? Most people know to tell me 2, right? What an absolute value is really doing is, when it's just x in there, is it's actually giving you the distance a value is from 0, right? So 2 is 2 units to the right of 0. Negative 2 is 2 units to the left of 0. But the absolute value just says, I don't care about right or left. I just want to know how far it is. Right? So that's why everything comes out as positive. Okay? Visually, what's happening when you graph an absolute value, if you look at the expression inside the absolute value bars, right? That's just x. Well, the line y equals x, right, looks like that. It would just go all the way up that way. So what the absolute value does graphically to a function is any parts of the function that are already positive just stay where they are. Any parts of the function that were negative get reflected over the x-axis so they become positive. So this piece of the line, y equals x, gets folded over, and that's why it points up like this. Okay? So if you wanted to write the absolute value, it's actually a piecewise function. And we say, well, it's just the line y equals x, because that's what this is, and this part of the line has a slope, right, of 1, when x is greater than or equal to 0. You would just plug it in the line y equals positive x. But when x is less than 0, it's actually the graph of the line y equals negative x, which should make perfect sense based on what we just said. If you multiply, right, a function on the outside by -1, it flips it over the x-axis. So that's what this did, right, when x is less than 0. So over here, right, it's a line with a slope -1. So one of the fun things that students will get a lot is, let's look at the graph of a parabola. So this is, we'll say the graph of -x² + 1. So a standard parabola x squared, it's on your base graph, is just a u that opens up, right? And the vertex, right, which is where the turning point is typically at the origin. So the negative in front of the x squared flipped it upside down. That's the first thing that happened. Then the plus 1 on the outside shifted it up one spot. So the graph of negative x squared would have had a vertex right here going through the origin, because we would have just flipped the original graph over, then we slid it up one. But what if I want to graph, I'll try to use a different color here, green. Right? What if we want to graph y equals, right, the absolute value of that function? So you don't always have to be given the equation. They could have just called this graph f of x and then said, now graph the absolute value of f of x. So the technique is the following, right? Everything that's positive stays positive. So everything above the x-axis here, well, that just stays where it is. That's going to be unchanged. But everything below, all the negative y values, are going to reflect up over the x-axis. So now anything that was negative will become positive because of the absolute value. So that's all you have to do. You just take any negative portions of the graph and you flip them up over the x-axis. All right, let's look at one more. All right, I was like this. So this is a very ugly drawing of sine of x, right? And if I want to graph right, the absolute value of sine of x. So the absolute value of sine of x, well, you leave, right, all the pieces that are above the x value, or x-axis, excuse me, they just stay positive, because any one of these y values that was already positive, absolute value is going to keep it positive. The negative values, right, go to the exact corresponding spot, or you just reflect them over the x-axis. So the absolute value of sine of x looks like this scalloped pattern, and everything lives above the x-axis. The absolute value of the sine of x would look the exact same way, except instead of having a cusp right here, you would have one of these maximums right here, because cosine starts right at a maximum. So in theory, and this is something Alex, I was looking through the homework last night, there's a lot of absolute value stuff kind of sprinkled in. So it doesn't really matter if you know the equation of the function. It doesn't really matter algebraically, but graphically you should be able in theory to graph any absolute value of any graph you see, but you just take the negatives and flip them over. So one thing that you'll see is, because of that, if you want to write out or graph an absolute value function, you have to turn it into a piecewise function, where one piece deals with all the things that were already positive, and the other piece deals with the things that were negative. So you'll always have a minimum of two things on a piecewise graph. For sine of x, sometimes we can split it in just the positive sections and just the negative sections. But for this guy right here, if I were to, no, we could do it here too. So usually what you do, like I'll show you how to write the piecewise graph for this. So the intercepts here, right, are going to be 1 and -1. So here's how we could write this as a piecewise function. The original expression is always used for the areas that were already positive. And so the way you specify when to use that is you get the intervals. So remember, this graph was already positive between -1 and 1. So we would just say, well, when x is between, right, -1 and 1, just use the original function, right? But when x is not in those values, right, we had to reflect the graph over the x-axis. So there's two ways we could write that. You can put the original expression in parentheses and just throw a -1 out front. That'll get the job done because it's multiplying by -1 on the outside. Or you could distribute the -1 across. And that's what I'm going to do. So if I multiply this expression by -1, I get x squared minus 1 when x is less than -1 or when x is positive or greater than 1. So you can write it as two lines where you have the domain for all the positive sections of the graph and you have the domain for all the sections that were originally negative. Yep.
Okay, so for on the test,
Mm-hmm.
when you're doing the graphs on the second one, you like reflected it exactly, but on the first one, you kind of made it look more like a V when you did it. Is that going to matter?
What do you mean? I mean, look at
How
look
it's
like a
a
V.
upside down U, and then when you drew the absolute value of it, you kind of made those lines go straight.
Oh, it didn't like it. Well, they do. They are. Oh, I see what you're saying. There's a little bit of a curve here.
Yeah.
Yeah,
Does
yeah.
that
No,
matter?
I'm not that picky. I was just, yeah. When you're hand drawing stuff, it's kind of hard to make it curve, but it's not a dramatic curve anyway because a parabola, it's curved around the beginning, but it does tend to straighten out as it goes. It's a very wide U, but yeah, no, that's fine. That's not a big deal. Yeah. And I mean, you saw my sine graph. It was ugly. Yeah, no, as long as you're getting the main, idea, I'm not gonna like in circles, like some people draw me circles that look like eggs. I'm like, as long as things are labeled correctly, I get it. I'm not testing you on drawing a perfect curve. But yeah, no, that's fine. That's, as long as you label the appropriate things, we're good. Okay, all right, so I had a really good problem. I want to show you guys.
Okay, so is that just the domain for the positive graph and the negative graph?
Yeah.
Okay.
So if you want to express, like if you wanted to graph this, like by hand, you would have to be able to know, you'd separate it out. But all absolute value functions are essentially piecewise functions.
How come they don't have for the negative graph, it doesn't have the equal?
Oh, because this isn't the actual domain. The domain of this function is all reals, right?
Yeah.
So what I'm doing is I'm just giving the intervals for that section of the function in a piecewise function. So it's not, you could write it as a union, but typically we write it as an inequality when we write a piecewise function.
It's like -1 is less than or equal to x, which is less than or equal to 1, and then the other one's just less than.
Oh, well that's because, so what if I ask you to find y of -1? You have to know what row to go on. And if it's in both rows, it's not a function anymore,
Okay.
right? So that's why, and so even though they line up, right, even though that piece joins the other piece, you have to just pick. Now I could have said the first line is between -1 and 1 without the equal sign, and then put the equal sign in the next line. I just couldn't have had it in both.
That makes sense.
Yeah. And so what you want to imagine is there's an open circle right at the ends of these lines, and that open circle, like the dot on the other graph, just fits right in and closes it. It's almost like a puzzle piece that just locks into place. So if you had two dots, right, then you're getting 2 points, and then that would violate the definition of a function. Yeah. So when you draw it, it's going to look like a straight up, just a continuous function. There's no breaks. But yeah, the domain of both of these graphs is all reals, right? The range, right? The range of the original function here on a parabola was just going to be -∞ to 1 because originally the graph capped out at 1, right? But when I took the absolute value of it, well now the lowest value is 0, because it never goes below the x-axis, but those pieces we folded up, well they go off to infinity. So the range of the new function after we flipped it was 0 to positive infinity. Down here, right, the domain was all reals, the range was -1 to 1, but when we took the absolute value, we're only looking at the blue sections, and that's 0 to 1 included.
How come on the Alex, like on some of the graphs, there'll be like two lines, like one like this, and then one line like closed, one open, and then another graph on like I'm gonna explain. There's like two lines, and then when it asks for the range, it asks you to simplify it, but it's like two different graphs. Like I'd have to like draw it.
Yeah, I'd have to see a question to know what you're meaning, but like, I mean, there are like, it sounds like a piecewise graph, like a piecewise function.
Yeah.
Now remember, I gave you guys that funky little piecewise function where I had it look like a piece of a parabola, and then I had a line pickup.
Yeah.
And what I did was I purposely made the open circle on the line. I let the parabola exist at that point, so when you went to draw the range, it looked like you were supposed to draw two different intervals, but the top of the range of one, where 2 was included, it wasn't included on the other line, but we were like, that's okay, and so you had to join those intervals together. Yeah, all right. So now what I want to do is I want to look at some of these base graphs, and I want to show how we can sketch what's going on. Now, one of the things Alex will do, and this is something that you don't need me to show you how to do, but Alex is going to start all of this off by making you make a table of values and create the X's, create the Y's, plot the points, and connect the points. We've all been doing that since high school, right? Some of us even in like middle school, right? Connect the dots. So what I want to spend class time talking about is, well, how do you take that step beyond that, and how do we just graph it, you know, in a more sophisticated way? So obviously on the computer, being able to plot the points and draw the points, but on an exam, that's not a very good way of doing the function, right? You're not going to have a lot of time, and you don't want to spend all day plugging numbers into your graph. If you were able to use like a graphing calculator where you could very quickly evaluate, but on these little TI calculators you're going to use, you don't want to be sitting there plugging X and Y values into a quadratic 10 times trying to plot data points, right? So I'm going to show you how we can use what we know about shifts and translations to sketch a pretty good version of the graph. So let's look at something like this. So the first thing that you want to identify when you're looking at a function is, well, what base graph am I starting with? So hopefully, if you see the squared term around the x expression, it's a parabola, okay? And the base graph for a parabola is this second graph on the page, right? It opens up and it goes through the origin, okay? That's the vertex. So the next thing that I would want to look at is, well, what's going on the outside of this function? Well, here, the coefficient in front of x squared is 1. The coefficient up there is still 1. So we haven't stretched the graph vertically, and we haven't flipped it around anything. So it's good. We don't have to do any flips. So that means this guy is still going to open up, right? Furthermore, when we're talking about a parabola, if there's a coefficient in front of the square term, if that coefficient is positive, then we know the parabola opens up, because that's what the standard parabola looks like. If that coefficient is negative, well, multiplying a function on the outside by a negative number flips it over the x-axis, so we know that that parabola opens down, okay? So here, we're going to have a parabola that opens up. This -3 shifts it to the right 3 places, and the 4 shifts it up 4 places. So what you do is there's always usually some distinct point on the base graph that everybody's supposed to know. So in a parabola, we usually talk about the vertex, and if you know on a base graph the vertex goes through the origin, well then shifting right and going up 4 should have happened at every single y value on the graph. So that means the vertex of this new graph that we're looking at, the vertex should have gone from the origin to 3, +4. Because the x value got shifted right 3, so you add 3, right? And the y value got shifted up 4, so you add 4. So that's all you do. You can take an existing point on the graph that you know and add the values to the x values, add the values to the y values.
Wait, why would it be +3? Sorry.
Because when you subtract on the inside, right, it makes the opposite move, yeah. Yep. So think about it, if I set the expression x -3 = 0, right? Because I plug that in, when you solve for x, you would get +3. Yeah. So the algebra, when you do the domain stuff, is going to make it look backwards. All right, so then the only thing that you might want to check, yep, sorry.
That's only inside the parentheses.
Inside the function, yeah. So inside the function, it visually looks the opposite as it should, but things on the outside are direct moves, okay? So if we look at this and we want to graph it, right, we want to be a little bit more accurate, the other thing we have to deal with is we have to sometimes go, well, are there any intercepts, right? Because it's going to cross the x-axis, cross the y-axis. We know the vertex is in the first quadrant, so we can draw that, but we want to make sure we draw it coming down the right way. So let's find the y-intercept. So the y-intercept, you just plug x into the function, or 0 into the function. So if I plug 0 into this function, right, I'm going to get negative 3 squared plus 4, or 9 plus 4, which is 13. So that means point, right, 0, 13 is on my graph. Oops. If I set this equal to 0, I should get 2 points because we all know a parabola's got two sides that come down, so there's actually going to be two x-intercepts. So if we set the graph x minus 3 squared plus 4 equal to 0 and solve for x, well, we'll get x minus 3 squared equals negative 4. I might have a problem here. Oh, yeah. Then what we can do is we can actually FOIL out the, that's what we're supposed to do here. So, all right, so let me show you what's going on here. So there's two ways you can solve this algebraically, right? The first is, if that 4 was a minus 4, right, when I moved it over to the other side, it would become a positive 4, and then I could just take the square root of both sides and keep going with the algebra. But because we have a negative 4 here, I can't take the square root of both sides. So the only other algebra option I have is to expand this out and move this back and create a quadratic. So if we FOIL this out, right, we're going to get x squared minus 6x plus 9, right, equals negative 4. So if I bring the 4 back over, right, and then what I could do is I could try to factor this, but it's not going to factor because 13 is prime. It's just not going to factor nicely. So I can actually use the quadratic equation. So x will equal negative b, right, plus or minus the square root of b squared, which is 36, minus 4 times a times c. Oh, good God, I'm a moron, guys. What does this graph do? I said it at the beginning of the problem.
It's a parabola.
Yeah, but how does it open? Up. So if the vertex, which is the bottom of the graph, is at 0.34, is it ever going to cross the x-axis? No. So if you're a big dummy like me and it's tired and you haven't had your coffee this morning, or your coffee hasn't kicked in, right? I can immediately see. So does everybody know? First here I saw, this is actually good. I'm glad this happened. So, because this happens on tests sometimes. First thing I saw, the first roadblock that I was like, wait, something's wrong because I can't keep going with this problem, right? The next thing also, you have a squared term equaling a negative. That's never going to be true. This is a false expression. Then when I started to do the quadratic equation, the other red flag I just noticed, well, I know 4 times 13 is bigger than 36. I would get a negative under that radical. So what this problem tried to scream at me 2 different ways and I wasn't paying attention to was that there are no x-intercepts. It's totally possible. They don't have to exist. Okay? So that means we have everything we need to know to graph this guy.
But if like it was if it was minus 4, wouldn't there be x-intercept?
Absolutely. Yeah.
Only if it's a positive.
Well, no, not necessarily, because if we'd had, let's see, what would we have gotten? If that had been yeah, because what would have happened is, and minus 4 would have shifted it down 4, and it could have shifted it below the x-axis. Yeah. So here's how we can graph this. There's 3, 4, right here. This is obviously not going to be to scale, right? We had a y-intercept, of 0, 13. And so this parabola, right, is doing something like that. So its vertex is in the, and so the original vertex, right, was down here. at the origin, and so we shifted it right 3 and up 4. Because you're allowed to make those moves in any order, you could have also said, well, I'm going to shift up 4 and then 3, and you would end up in the exact same spot. So one of the things that's kind of neat about the Graphing Utility Online Desmos is sometimes there's a way you can set it up where you can actually grab the graph and actually drag it around on the graph. Where in ALEKS, what you have to do is you have to plot. You have to first identify what type of function it is, plot 2 points on the function, and then you use a connect feature to connect them. So if it's a line, you just plot the 2 points and connect. If it's a parabola, what you usually do is do exactly what we did. You plot the vertex, and then you plot another point on the parabola. And so when you click it, it knows to put the vertex through that point and connect through the other. And then you'll see later when you get deeper in the class, they have other buttons to do things like waves and stuff like that. All right, let's look at another one. I want to look at a graph that I gave you guys earlier when we talked about functions. The square root of x plus 1. So the square root of x can't ever give you negative values outside of the function, right? So if we're looking here, well, the base graph is just the graph of the square root of x. And the square root of x, you're allowed to plug in 0, right? They get bigger, right, as you plug in bigger values. So this is what that graph looks like. So what is this function doing now? It's taking the square root of x and doing what to it? Shifting it to the left 1 unit, right? Because that move happened on the inside of the function. So if you want to sketch it, right, the value that was at 0, 0, well, we just move it left. So now it's at negative 1, 0. And then if you want to know what that intercept is, well, you just plug in 0 for x, and the square root of 1 is 1. So we can very easily see, right, that is 0.01. All right, so let's flip something, because we haven't done that yet. Let's look at the graph of negative 1 over x. So if you look at this guy, what is the value of x that's not allowed? And if we look at the base graph of this is just 1 over x. So if you look at the graph of 1 over x, this should make sense. So at x equals 0, you have a vertical asymptote. So usually any values of x that would make the denominator 0, graphically that a lot of times translates into vertical asymptotes at that x location, because it's never allowed to get there. Also, what happens to a fraction when you make the denominator bigger? It gets smaller, right? So look what happens to this function as x gets really, really big, the value starts getting closer and closer to 0. Okay? Same thing's true in the negative direction. If you divide by a really big negative number, right, it stays negative, but it still gets closer and closer to 0. So just looking at the structure of the original base graph, you kind of make sense why you have a vertical asymptote at 0 and why you also have a horizontal asymptote at 0. So if I multiply by negative 1 on the outside, what is that supposed to do to the graph?
Flip it over the
X-axis, right? So it's taking all the y values and making them negative, so it's flipping it this way, okay? So if we draw this now, well, the piece of the graph that was up here in this quadrant, right, now comes down here and lives in this quadrant. The piece of the graph that was down here in quadrant 3, well, it got folded up, and it now goes up and lives in quadrant 2. And so that's all we did. We took the original graph and flipped it upside down, okay? All right, so we'll stop here for today.